Now we go on to a new topic, which can go under the general rubric of placing objects into boxes. Okay, so let's start with an example. We have a few different types of examples here, and they'll all really reflect the same structure. So consider the situation of placing 8 identical objects into 3 boxes. Okay, so 3 boxes, and we have 8 objects. They're identical. So, and we want to put them into the 3 boxes. So, so there are many different possible ways we can do this. Some possible ways to do this are as follows. So here's one possible way. So the lines are the separation between the boxes, and the stars are the objects. So I can put 2 stars in the first box, and then there's a separation for the next box. And then I can put 3 stars in the next box, and then maybe 3 stars in the last box. All right, so that's one possible way of doing this, right? So 2 in the first box, 3 in the second box, and 3 in the third box. Here's another possible way. Maybe I put 3 in the first box, then 1 in the middle box, and then 4 in the last box. Or maybe I put 5 in the first box, I put nothing in the middle box, right? So I have this just nothing in the middle, and then 3 in the last box. Or here's another possibility. Maybe I put nothing in the first box. So I have nothing before the first line. Then I have 3 in the middle box, and then 5 in the last box. So those are 8 different ways of putting, those are a few different ways, 4 different ways of putting 8 identical objects into 3 boxes. So these are just some possibilities. Here's another possibility. Forgot about this one. Here's another possibility. Maybe I put all 8 into the first box, and then the middle box is empty and the last box is empty. That's also possible. So we can ask the question, in how many ways can this be done, right? In how many ways can I take these 8 objects and put them into 3 boxes? And keep in mind, it's possible that some boxes will end up with nothing inside them, right? Like here, or like here, there's nothing inside it, or like here, there's nothing inside the first box, or here, there's nothing inside the middle nor in the last box, right? So those are all possibilities. So in how many different ways can this be done? So the number of ways this can be done is equal to the number of ways to fill 10 positions with 8 stars and 2 bars. So what we're going to use here is we're going to use this type of diagram, stars and bars diagram. And so putting 8 identical objects into 3 boxes is the same thing as arranging these stars and bars on the paper. So the number of ways that we can put these 8 objects into 3 boxes is equal to the number of ways that we can fill 10 positions with 8 stars and 2 bars, right? Notice all these diagrams have 10 symbols, right? 10 symbols. They have 10 symbols. So there are 10 positions, and 8 of those positions are going to get the star symbol, and 2 of those positions are going to get the bar symbol. So we have 10 positions. We need to fill with 8 stars and 2 bars. So again, the number of ways that we can place 8 identical objects into 3 boxes is equal to the number of ways to fill 10 positions with 8 stars and 2 bars, as in these diagrams. So the question is, how many such diagrams can we make? So there are 10 choose 8 ways to pick the positions for the stars, and the rest must be bars, right? So if I'm trying to make a diagram, I want to make a random diagram like this. So I have 10 slots to fill, and 8 of them must be stars. I don't care about the order of the stars because they're all identical to me. So I can put the stars in any order I want. So there are 10 choose 8 different ways to pick the positions for the stars. And then once I do that, the only 2 open slots must be bars. So the answer is 10 choose 8, which is 45. So the number of ways of placing 8 identical objects into 3 boxes is 45. Now you might say, well, hold on, how do I know to start off with stars? And then the rest are automatically bars. Maybe I should start with bars, and then the rest will automatically be stars. So let's try that. Alternatively, we could first choose the positions for the bars and then fill the rest with stars. This leads to the same answer because it gives us 10 choose 2, which actually is equal to 45, just like 10 choose 8. Okay, so we can do this in either way, but we'll get the same answer. So note that the two answers are in fact one and the same. So it's not like there are two answers to this question. No, there's one answer to this question, which is 45. But there are two different ways we can express it. We can express it as 10 choose 8, or we can express it as 10 choose 2, but it's the same thing. Okay, now we can talk about a new type of object. We've talked about sets, we've talked about lists. Now we can talk about something similar, something sort of similar to both of them in a way, multisets. So a multiset is a collection of elements in which order is not significant. Okay, so far it's like a set, order doesn't matter, but duplicate elements are allowed. So that's not like a regular set. A regular set cannot have duplicates, but a multiset can have duplicates. Now, if A is a multiset, we denote its cardinality. Its cardinality, which is denoted like this, is the number of elements that it has, counting duplicates multiple times. Okay, so in this way, it's a little similar to a list where the length of a list, to get the length of a list, we count the number of entries, even duplicates. So here we count the duplicates as well, count the duplicates multiple times. So a simple example, here's a multiset, we can call it A, and we write a multiset usually with square braces instead of, square brackets instead of curly braces, and not parentheses either. So 3, 1, 1, 3, 5. So it's a multiset, right? Because it's the order doesn't matter, but duplication is allowed, right? So to point out the idea that order doesn't matter, these two things are in fact the same multiset. This is equal to this, right? The order doesn't matter, as long as they have the same elements. The cardinality of A is 5, right? So we count the duplicates multiple times. Okay, now we're going to use stars and bars, the thing that was introduced very recently. We're going to use them to count multisets. Okay. So let's say we have the set A, B, C, D. Question. First, let's ask, before we talk about multisets, let's talk about sets. How many sets of cardinality 5 can be made from the elements of S? So if I want to make a set of cardinality 5 using these elements of S, how many such sets can I make? Well, the answer is 0, because a set cannot have duplicates. So how can I make a set of 5 elements using only 4 objects? With, a set doesn't allow repetition. Okay, so now we can ask how many multisets of cardinality 5 can be made from the elements of S. So here the answer is not 0. Right? The answer is not 0 because the multiset is allowed to have duplicates. So what's the answer? So there are many possibilities. Before we get to the answer, let's just show some of the possibilities. So here are some possibilities. Right? We can have A, B, C, D. That's a multiset. It has cardinality 5, and it's made using only the elements of S. Here's another multiset. Here's another one. Okay. Now what we're going to do is write these multisets in a shorthand. Now I want to point out that I wrote all these multisets in alphabetical order, and that's fine. And I don't lose out anything by doing that, because in a multiset, the order doesn't matter, right? So I can decide I want the order to be I want to write it out in a specific order. It's not like I'm not going to be forgetting about anything that is in a different order because the order doesn't matter. So the idea here is we're going to write these multisets in a different fashion. So we're going to turn these into this. So for example, for this one, this is A, B, C, D. So we're going to write A, and then a bar, and then a B, and then a bar, and then a C, and then a bar, and then D. So the bars are going to separate between the different letters, right? So the AA goes together because they're both A's, and then we have a bar to separate from the B's, and then another bar to separate from the C's, and another bar to separate from the D's. So this second multiset example, the second example would become this, right? So we have AA, and then a bar, and then nothing after that because there's no B's, and then a bar, and then the 2 C's, and then another bar to separate. Oh, this is a mistake. This should only be 1 bar. Okay, so now this is fixed. So So again, this multiset A, C, C, D becomes AA, and then a bar, and then nothing after that because there are no B's, and then a bar, and then two C's, and then a bar, and then the D. This last multiset would become, so there's a bar, there's nothing before the first bar because there are no A's. Then we have the bar, then the B's, and then a bar, and then nothing after that because there are no C's, and then a bar, and then the D's. Okay. So now we're going to go a step further. We're going to turn these what we just wrote, we're going to turn these into stars and bars diagrams. So these are going to become, so what we're going to do is we're going to have, here we're going to have two stars for A, and then a bar, and then a star, and then a bar, and then a star, and then, just instead of writing out the letters, we're just going to put stars. Okay, so it's like that. So we can represent every possible multiset of cardinality 5 made from the elements of S in this manner, right? So what we're doing here is we have 8 positions, 1, 2, 3, 4, 5, 6, 7, 8, 8 positions holding 5 stars and 3 bars, and every possible multiset of cardinality 5 made from the elements of S, which is what we want to count, every such possible multiset can be represented in this manner, right, using stars and bars. So we have, but keep in mind, we have 8 positions. We need to fill them with 5 stars and 3 bars. Any way, any random way we do it counts. So in other words, the idea is we have certain, the first few stars before the first bar represents the number of A's. Now there might be 0 stars before the first bar. That means there are no A's, right? So that's also possible. So there's an unknown number of A's, meaning an unknown number of stars before the first bar. And then we have the first bar, and then we have an unknown number of stars for the B's, and then a bar, and then an unknown number of stars for the C's, and then a bar, and then an unknown number of stars for the D's. The total number of stars and bars in the diagram is 8, right? There are 8 symbols that we're using in this diagram. How many such representations is it possible to make? In other words, how many such multisets is it possible to make? Because each representation represents one multiset. So the answer is 8 choose 3, because we have 8 positions and we need to choose any 5 of those in any order to be the 5 stars. Or actually, as I do it here, we need to choose any 3 of them to be the bars. Okay, so we can choose the stars or the bars, it doesn't matter. But again, we have 8 positions. We need to choose any 3 of them and in any order to be the positions for the 3 bars. 8 choose 3 is 56. But we could also do it the other way. We can also say 8 choose 5, right? We can also say we have 8 positions and I need to choose 5 of them to hold the stars. And the rest will just automatically be bars. That also is valid. But either way, the answer is 56. So there are 56 multisets of cardinality 5 that can be made from the elements of S. Here's another example using stars and bars. How many non-negative integer solutions does the equation w plus x plus y plus z equals 20 have? So this is an equation, right? W plus x plus y plus z equals 20. And we want to look for non-negative integer solutions. So solutions that only involve non-negative integers for w, x, y, and z. And we want to know how many different possible solutions are there. Okay, so we're going to see that we can do this using stars and bars. So here's one solution, and I represent it as a list. So the first thing is w, then x, then y, and then z. So let's say w is 3, x is 4, y is 5, and z is 8. That's a solution. Why? Because 3 plus 4 plus 5 plus 8 is equal to 20. Okay. How about this? Is this a solution? 1, 2, 3, 5. This is not a solution, as the sum is 11, not 20. How about this? Is this a solution? -1, 1, 5, 15. If you add it up, it equals 20. But it's not a solution because it contains a negative number. So we're only interested in non-negative solutions. So the idea here is to represent a solution using stars and bars. Here are some examples. Let's say we have this solution, 3, 4, 5, 8. That's a solution. So we're presented with 3 stars. Okay. So that's telling us the value of W, right? These 3 stars are telling us the value of W. W is equal to 3. Then we have a bar, and then the next few stars tell us the value of X. So in this case, X is 4. Then we have a bar, and the next few stars tell us the value of Y, and then the next few stars tell us the value of Z. Here's another example. So we might have a solution 0, 0, 10, 10. This is a valid solution because 0 is not negative. So 0 plus 0 plus 0 plus 0, 0 plus 0 plus 10 is 20. So this is a valid solution. We would represent this by having nothing before the first bar because W is 0. We also have nothing after between the first bar and the second bar because X is also 0. And then after the second bar, we have 10 stars for Y, and then we have a bar, and then we have the last 10 stars. The last 10 stars for Z. Okay, so every possible solution to this equation can be represented using a star and bars diagram like this. So the idea is that if we want to count how many solutions there are, we can simply count how many stars and bars diagrams we can make. So we can represent every possible solution in this manner. So notice that there are going to be 23 positions in every stars and bars diagram for this example. 23 positions holding 20 stars and 3 bars, right? 3 bars in the middle, and then somewhere in there, and then the rest 23. So 20 stars and 3 bars, and total of 23 symbols or positions to put down symbols. So the idea is like this, the first few stars represent the, I'm sorry, this is not A, this should be W, X, and Y, and Z. Okay. This should be W, this should be X, this should be Y, and this should be Z. Okay. Anyways, making believe it says that. So the question is, how many such representations, in other words, how many solutions to the equation is it possible to make? Because a representation is just a way of representing a solution. So if we talk about representations, and if we count the number of representations, that means we're counting the number of solutions. So the answer is, well, we have 23 positions, and we need to choose 3 of them to be bars. So that's 23, choose 3. We don't care about the order of the bars, so it's 23, choose 3, which comes out to be 1,771. Or we could also look at it the other way. We can say we have 23 positions, and we need to choose 20 of them to be stars. So that's 23, choose 20. Either way, it comes out to be the same.